Thanks, everybody. I'm really excited to be here. This is my second time in Fairbanks, and I came at a different time. When I first came to Fairbanks, it was actually during a time called solar minimum, not so much Aurora. And it's approximately about the same time, got to go to Poker Flat. And now I'm back during an important period for solar physicists called solar maximum. So that's what I'm going to talk about today. And so the part about the aurora is maybe not what you would think would be a normal aurora talk, because my focus is going to be on what's driving the aurora, that is the sun, and in particular talk about sun's activity and its cycle. Okay, so this is sort of the backbone of the energy that is pumped into our near-Earth environment that's driving the aurora, but I won't focus as much on the aurora. So first, I'd like to give you a little bit of an idea of how I got into science and how I ended up being at NASA. So this is sort of the things that drove me. First and foremost was I didn't want to be Captain Kirk. I wanted to be Dr. Spock. I should say Mr. Spock. And at the same time, it was when the Voyager spacecraft had been launched and the beginning of the space shuttle program, and of course the original Cosmos with Carl Sagan. And then that's me at Kennedy Space Center for the launch of the Parker Solar Probe, which is the first probe that we have sent through the sun's outer atmosphere. And at the end of this year, it will make its closest approach December 24th, 2024. And one of the things that I know many of us have been a little bit disappointed about is the lack of aurora over the past many days. And I know that I came here looking forward to it and still have my fingers crossed. But, I also have really been excited about the opportunity to start learning a little bit about the local culture. And fortunately, my wife was able to take a video of some of my recent experience at the beginning of my visit. So let's see. So there's me waving in the back. So that was my introduction to mushing. I actually did get to stay up for a little bit longer on the sled during the rest of the time, but it was an amazing time, a lot of fun. So we're going to start with the solar system. So at the middle of the solar system is the sun, makes up most of the matter in the solar system, about 99% of it, and around it are for most people today, it's the 8 planets. I still personally feel like it's 9 planets. So Pluto, I grew up with Pluto, so what can I say? But I want to show you a little bit of some size comparison to just get a feel for how big and how massive the sun is. So we'll start off with the Earth-sized planets. So Earth, Venus, Mars, Mercury, and of course, little Pluto. And then if you move out past the asteroid belt, we have the gas giants, and actually we really don't call Uranus and Neptune the gas giants, but really we call them ice giants. And so you can see Earth down here, some scale especially with Jupiter. And now, if we put the sun in the picture, there's the Earth. If you took this Earth, you could put about 108 of them side by side across the diameter of the sun. So it's just a massive object. And at its core, because its gravity is so intense, it is squeezing its hydrogen to the point that it's actually fusing, releasing energy. And that's the energy source which is driving the sun and actually drives all stars. So when we think about the sun here on Earth, I think most of us have probably heard that, you shouldn't look at it, it's too bright. This is really about the most that we can get. Maybe during a sunrise or sunset, you can see a little bit more, but it's not particularly interesting. But the one thing that I want to put in your mind is to think about every time you go out at night and you look up at the stars in the sky, that just think that each one of those is very much like our own sun. It's our own very own star. Some are a lot bigger, some are a lot smaller. The sun is kind of in the middle, sort of a medium size, but each one of those little dots is basically like the sun that we're used to every day. And then when we talk about the dynamics of the sun, there are three main elements that are important that are driving the dynamics. So I want to step you through those. So the first one is magnetism. So maybe you remember having a bar magnet and putting some iron filings around it. It actually shows you the invisible magnetic fields. These are the magnetic fields that will stick a magnet to your refrigerator. But this is something we're going to come back to. So first part is magnetism. That's a very important key part. Now the next part are plasmas. We are not super used to the idea of plasmas. This is the fourth state of matter. But if you start off with a solid and then you heat it up enough, it turns into a liquid. If you heat it some more, it then turns into a gas. Well, if you heat it a lot more, that gas actually turns into a unique type of matter that's very much like an electrical or ionized gas or liquid. And it has all kinds of crazy cool properties that make it very interesting. But it's basically impacted or affected by magnetic fields. So that's a key part. So unlike a regular liquid, this is going to respond to magnetic fields. But you can see some of the examples, things like nebulas, but closer to home, lightning, even the aurora themselves. And this is just a special type of incandescent light bulb. All of these are examples of plasma. Basically, a lot of these are where you have a gas and you put electricity through them that heats them up. So together, magnetism is an integral part of plasmas. Plasma is an electrodynamic type of gas or liquid. And so plasmas are basically, they have electrical currents in them when the particles move. So when you combine plasmas and magnetic fields, this is key to the structure of the sun, and I'll show you what I mean by that. But the main thing that I want to point out is, think about the fact that when the sun moves, when the material of the sun moves, which is a plasma, it pulls those magnetic fields with it because they stick together, kind of sticks to each other. So that's a key part. So there's one last feature that's important, and it has to do with the motion, the rotation of the sun. So, for example, the two gas giants, Saturn and Jupiter, they're not solid bodies through most of them, and when they spin, you see those little structures, those bands. Well, those happen because they actually spin faster at the equator than they do moving towards the poles. Okay, so remember, the sun is like that. So the sun is going to do the same sort of thing. So we have the sun is a plasma, the magnetic fields are connected to that plasma, and it has this weird type of spinning where it's rotating faster at the center. So what does that do? So watch this. First you have magnetic fields like this. But you see the equator, it's moving faster. It's dragging those magnetic fields around. And eventually they get bunched up, they get knotted up, kind of like a rubber band, and they start popping through the surface. And where they do that, where they come through the surface, you have sunspots. Sunspots are areas of really concentrated magnetic field. So here's an example. This is the sun in visible light from space, and there's a giant sunspot. Remembering that you could put 108 Earths across. So this is really big. This is several Earths in area, in size. We can zoom in on that to get a little bit more idea of the scale. So if I zoom in on this area, there's the same sunspot with an Earth, just to show you the scale. But this whole thing are these magnetic fields poking through the visible surface. So those are key pieces to what's driving the sun's activity, what's making the sun interesting. And to give you some comparisons, this is actually a little thing I put together back in 2014. During this particular time, the sun was incredibly active, what we call solar maximum, which I'll talk about for now. And this is to give you a size. We had a sunspot that was about the size of Jupiter. Okay, it was massive. And so why is that interesting? Well, the thing that's important here is that magnetic fields have energy. So again, think of it like a rubber band. If I take a rubber band and I start to twist it and continue to twist it, you're building up energy in that rubber band. And eventually, it's going to start knotting up. And if I do it enough, that rubber band will snap. And that releases the energy. And magnetic fields do something very similar to that. So that's a key point to remember. There's a huge amount of energy in these sunspots. Now, talking about how sunspots change over time, it turns out that people have been counting sunspots very regularly since the 1700s. They certainly have seen them earlier than that, but there's been a concerted effort to count them and have as accurate a measurements as possible. But here's a recent look. So over that time period, we started numbering these little humps, okay? We call this a sunspot or solar cycle. So right now, we're actually on number 25. So this goes up to 24. But you can see that they're roughly the same length over time. Some are a little bit bigger, some are a little bit smaller. They basically are about 11 years in length. Okay? On average, they're 11 years. And we call that the solar cycle, going from very few sunspots to a lot of sunspots back down to very few. And so here in the valley, this is solar minimum, the minimum of activity. And at the top, it's the maximum. And it turns out, right now, for cycle 25, we're somewhere close to the peak. Maybe even in the peak. So I'll talk more about that. Now, in 2019, during solar minimum, there's a panel that gets together and predicts the next solar cycle. Okay, they take all the past data, they do various hand waving, a little bit of statistical magic, and they try to predict what the next solar cycle is going to look like. So at the end of solar cycle 24, this was the prediction of solar cycle 25. Now we are actually about right in this area here. So how does this current solar cycle add up and compare to what the prediction was? And so I will get to that, but first I'm going to talk a little bit about what does the activity, what does this increase in sunspots really mean? What kinds of things do we see because of that? But there's a little bit more to this because it turns out that there's another cycle, not just the sunspot cycle, there's actually a magnetic cycle. So if we take a little bit more data, so I'm going to look at the sunspot numbers. Okay, so we're counting sunspots. So like right here, the sunspot number is 50. It's not exactly counting like 1, 2, 3 sunspots. It's actually scaled number, but we can think of it that way. So if I look at, here's some more data. Okay, so now here's the sunspot number. And so this is actually more cycles, 15 up to 24. And you can see this cycle from here to here is roughly 11 years. Okay, that's one cycle. But if I look at the magnetic field of the sun, of the northern part of the sun and the southern part of the sun, I measure those magnetic fields from Earth and I put them on a timeline, you see this pattern. So here's the northern. Now it's a little bit confusing because we picked a point where we said, okay, the magnetic field here is the north, the magnetic field here is the south. But let me also, you can think of this as positive and negative if you want, okay? Basically, they're just opposites, okay? That's the important point here. But, so this particular magnetic field goes like this. And the opposite one on the other pole. So we measured it on one pole and the other pole, okay? The other pole, whoops, starts here and goes like this. So you see they go up and down. And so it turns out that one magnetic cycle is twice that. And so why is that? Well, what's happening, what this means is the magnetic field of the sun increases, and then right here, what this means, where they cross, it means they're moving in opposite directions, okay? So right here, the positive or the blue is up, but here it's down. So it's flipped. The magnetic field of the sun has flipped. And so what we're interested in is where it flips and then goes back. So this is a little, I should put a little dotted line here, but so I'm actually looking at, my laser is dying. I'm looking at right here to right here. It turns out the flip happens at the same time that the sunspot cycle is a peak. So they're shifted, okay? So when the sunspot cycle is at its highest, the magnetic fields of the sun do this. So that's 11 years, okay? And then at the next cycle, another 11 years, they flip back. That's the magnetic cycle. Flip, flip. So it's twice the solar cycle. And we don't fully understand all that, but there's all kinds of really interesting things happening. But what we've learned is there are two cycles. And really, the underlying one that's driving everything is the magnetic cycle. So again, it comes back to magnetism. So I wanted to show you this just to remind you, one of the things that's very important in all areas of astronomy is looking at objects in different types of light. And light is not just the visible light that we're used to, but there are other kinds of light. We've all heard of ultraviolet light. We can't see it with our own eyes, but it burns our skin. There's X-rays, gamma rays, and then in the other direction we have infrared, which is basically heat, microwaves, and radio. So you can see that light actually covers a huge range of different types of energy, types of light, okay? So that's one of the things I wanted to point out. And the reason is because it turns out that there are a lot of really cool and important things you can see from the sun if you look at other wavelengths besides visible light. If you look at ultraviolet light and X-rays, it's a lot more interesting. There's a lot more going on. So let's look at the sun in different wavelengths of light. So this is, again, visible light. This is the light we're familiar with. Okay, this is the kind of light that our eyes can see. But the other thing is, what we also know is that the type of light tells us something about the temperature. Okay, so right now, when we look at the sun in visible light, it's giving us roughly a temperature of 6,000 Kelvin. Now, Celsius and Kelvin are not exactly equal. However, at these temperatures, they're very close to equal. So I'm just going to call them the same thing. So this first layer, the visible layer of the sun, is 6,000 degrees Celsius. And we're going to start moving up to higher and higher layers and see what's happening. So this is a little bit higher. This is ultraviolet light, and the temperature drops a little bit. And we're used to that, okay? If I'm standing next to a campfire and I feel the warmth as I step away from it, the temperature is going to go down. I mean, that's what we would expect. But something really weird happens on the sun. As I move to the next layer, it actually gets hotter. And then it very quickly starts getting really hot as I move higher and higher. And by the time I move to the outer part of the sun's atmosphere, actually the part you see during a total solar eclipse called the corona, the temperature can get up to, actually it can get even higher than this, sometimes up to 20 million degrees Celsius. Very, very hot. But you'll also notice, let's go back to those sunspots. So the sunspots change. So they're dark here, but as we get to higher and higher temperatures, they're bright. And that's because those sunspots, over top of them, they have magnetic fields, which have a lot of energy, and so they get really, really hot. And that's actually where all of the interesting stuff is going to be coming from, predominantly from the sunspots. So I'll show you some examples again to look at what we call solar min and solar max. Remembering solar minimum is when there are very few sunspots. Solar maximum is when there are a lot of sunspots. So this is solar minimum and this is solar maximum. I know the dates are backwards, but blame it on NASA. This is looking in that ultraviolet wavelength. This is actually showing as 600,000 degrees Celsius. This is solar minimum. You don't see a lot here. But here, where all those sunspots were, you can see all of this exciting stuff going on. And these are actually loops of magnetic field. Remember when we took the bar magnet and you put iron filings around it, you could see those invisible lines. Okay, well, the sun, because it's made up of something that's electric that responds to magnetic fields, it actually traces out and highlights those loops. So you're looking at giant loops bigger than the Earth of magnetic field that have lots of energy in them. So now I want to go back to, again, talking about the solar cycle. So remember I showed you the solar cycle estimate by the panel, which is a NOAA-NASA panel, okay? What they said was solar maximum is going to be middle 2025, and it's going to be about the same size as the last solar cycle, maybe even a little bit smaller. That's what they determined. Well, okay, so here is solar cycle 24, and here's solar cycle 25. This is where NOAA and NASA panel predicted, that blue line. You can see it's far surpassed that. It's actually probably going to peak right around here, may even has reached a peak this year. The other crazy thing is, if you may have noticed in some of those other plots, some of those peaks had little double humps. I don't know if anybody noticed that. Turns out that the north and south hemisphere of the sun sometimes reach their peaks at different times. So a lot of solar cycles actually have a little double hump. So one hemisphere than the other one. And right now, there's actually a peak in the northern hemisphere, but the southern hemisphere doesn't appear to have reached its peak yet. So it looks like we're going to have another double hump on this solar cycle, and it's going to be much bigger than we expected. It's far surpassed what was predicted. So this is the sun now. Looking at it, I've taken several of those ultraviolet wavelengths, 3 different ones, and I've put them together in this one video. It's all the same time period, but look how dynamic this is. Look at all the stuff that's happening. So you see there's a flash. That flash is a flash of light over the whole electromagnetic spectrum, and that's called a solar flare. And all of this stuff you see moving around are billions of tons of solar material that's been blasted out into space. So I'm going to show you some animations in a second of what that actually looks like. So here are the sunspots, and you see these magnetic fields coming up out of the surface, okay? This is below, and you see the magnetic fields start to rise up, pop through the surface, and they actually appear dark. And as they move up, eventually, they snap and they release that energy. There was the flash, the flare, and you saw it push stuff above it. That's that big blob of material. Billions of tons of solar material. We call those coronal mass ejections. That's mass that's ejected from the corona. And this is another animation. So you see there's the coronal mass ejection. Looks kind of like a croissant. And it turns out that, trying to make sure I'm within the camera here, okay. So that big coronal mass ejection, that big blob of stuff, when it comes blasting out of the sun, it actually creates a shock wave, kind of like a snowplow pushing the snow, and then it creates particles in front of it that get accelerated to super high speeds. So what you saw there is you're going to see the flash, there's the flare, okay, and here's that stuff coming out, and it's pushing things in front of it, and it makes this big spray of particles, which basically amounts to high energy radiation, high energy particles. And so here they come. So the Earth has a magnetic field, and these particles are electromagnetic, so they hit the Earth's magnetic field, but a lot of them get deflected around it. And here's another perspective. Now, this is actually real data, a real visualization of real data. So you see there are particles coming from the sun all the time, and then all of a sudden there's this big blast. That's that big blob of stuff pushing the particles in front of it. And all of that energy, the particles and the material, slam into the Earth's magnetic field and basically kind of ring it like a bell. And when that happens, it creates all of these complicated electrical currents in the upper atmosphere. And so here's an example. One of the things is stuff from the backside of the magnetic fields actually is slingshot into the poles. And when that happens, these particles come into the North and South Pole, and they slam into our atmosphere, and they give us the aurora. So here's another little animation of that. So the particles are going to travel along these magnetic fields. They're coming from the back part of the Earth's magnetic field, and they're going to be channeled down into the upper atmosphere, and they're going to slam primarily into oxygen and nitrogen. Oxygen will give us the greens and the reds, and the nitrogen gives us kind of the bluish, purplish. Okay, so those are animations of what can happen, okay? Remembering that these magnetic fields get all twisted up. They get all knotted like a rubber band, and they snap, and they release energy, and that creates that flash of light called the solar flare, and it pushes stuff away, billions of tons of solar material called the coronal mass ejection. And sometimes they can create those particles in front of them. So back in 2000, mistake, 2023. Yeah, sorry, that's a typo. That should be 2003. So does anybody remember Aurora in 2003? Okay, you remember. Well, it turns out in 2003, there were a couple of really huge sunspots. First of all, that came out of nowhere. They just came up through the surface. They quickly grew in size to as big as approximately Jupiter. Really massive. Very complicated, meaning that they had a lot of energy built up in them. And over a 2-week period, they just went crazy. They started shooting off solar flares, blasting huge blobs of material, coronal mass ejections, and they created shock waves that were blasting out these high energy particles. So I'm going to show you some real data, first from an instrument called EIT on SOHO. Okay, it's an older instrument, but it's ultraviolet. So you're going to see all these flashes, you're going to see things happening. So we'll start with that. So this was over 2 weeks from the end of October to the beginning of November. So first, there are the sunspots. These actually grew very quickly. There's another one, all of a sudden just pops up out of nowhere. You see they're massive. So you see things happening over here. There's lots of little flashes, materials moving around. And it was just shooting off flares and these coronal mass ejections one after the other for about 2 weeks. And eventually, you'll notice all of that snow on the images. That's those high energy particles. Okay, so that is those particles that were pushed ahead of the coronal mass ejection, like the snow plow, that are slamming into the camera, into the CCD, creating all those little, that snow. And so this is a pretty good view, but it's really hard to see those CMEs, those big blobs of stuff coming out. So there's another way we can look at it using something called a coronagraph. And it's basically an artificial eclipse. So if I take a camera that's looking at the sun in visible light, but I put a disk in front of it, like the moon does during a solar eclipse, I can create an artificial eclipse. And it allows me to see very faint stuff around it because I've blocked out that bright disk. Now in this one, I've actually overlaid this image on it, on top of it, so you can see where the sun is supposed to be. But this is a coronagraph. So there's where the sun actually should be. And so you see all that stuff coming out. That's all those coronal mass ejections. There was a comet that just went in here really quickly. And then you see all the snow from those particles. So over that 2-week period, we had some of the biggest, actually we had the biggest solar flares ever seen in the modern space age, some of the biggest coronal mass ejections, and those created some of the largest magnetic disturbances here at Earth. And that created aurora that was seen all the way down to Florida. So here are some of the things that happened from those storms. So here are a few of the images of the aurora. There's one from Fairbanks. More than 20 satellites were affected. Half of NASA's fleet. We have no idea how many military satellites were affected because that's top secret information. There was a Japanese satellite, an astrophysical spacecraft that was lost completely. The reason being because when all of that energy is pumped into the Earth's atmosphere, it expands. And so if you have a satellite and all of a sudden the atmosphere expands, it's going to experience drag. And in this case, enough drag that it actually lost orbit. We had severe HF radio blackouts. This is the first time the FAA issued a radiation warning for passengers because polar flights see more of those high energy particles. And so those particles were extremely intense, and you could see that from the images. There was a power failure in the Swedish power system. Himalayan climbers were experiencing problems because their satellite phones weren't working. The Coast Guard's LORAN navigation system had to be shut down. But ironically, the radiation monitor on the Mars Odyssey was knocked out from the intense radiation. And lastly, part of the Martian atmosphere was blasted out into space, lost forever. So all of that energy and material that's coming from the sun is interacting with everything in the solar system. And this is why we pay so much attention. And of course, locations at higher latitudes near the poles experience especially intense aspects of this. So Fairbanks, of course, being one of them, and as Bob mentioned, a driving reason for the formation of the GI in the first place. And this is why we need to study it. From NASA's point of view, all of this material and energy is not just impacting Earth, but it's also impacting all the spacecraft that we're putting out into the solar system, all the way out to the very edge. And so it's important for us to protect those. And those high energy radiation particles you saw are dangerous for astronauts. We're very well protected here on Earth by our thick atmosphere and our magnetic field. But if you're on the ISS, or even worse, if you're on your way to the moon or Mars, you're completely exposed to all of that. And in fact, in 1972, between the last two Apollo missions, one of the most intense radiation storms ever recorded occurred. And if those missions had been shifted, then it's estimated that the astronauts would have possibly experienced fatal doses of radiation. And this is, I don't expect you to look at all of this, but this is just sort of an idea of all of the different kinds of impacts that all of this solar activity, the space weather environment that's created, can impact everything from various types of communication. The radiation can directly impact spacecraft. It can, of course, be dangerous to astronauts, to passengers on polar flights. And in the worst case, as I mentioned, for example, with Sweden, you can have power outages. Power grids can be overwhelmed with the electrical currents. And another example of this happening, very famous example, was 1989, Quebec power grid was impacted. But that actually propagated down into the Northeast, and there were transformers that melted in New Jersey because of that. So before I wrap it up, I just wanted to show you a little bit of some of the recent activity that we've had, not this week, but over the past week. I was hoping for some of this week so that we would have some more exciting auroral displays, but here are just a few things. This was actually a huge flare, so there was what we rate flares very similar to the way we rate earthquakes, and the largest rating is an X flare. This was a small X flare that occurred right here. However, it didn't create a CME. It didn't go towards Earth, but the radiation, the particles, actually, because they follow magnetic fields, they made it towards the Earth. And you see a lot of the, whoops, sorry about that. You see a lot of the snow on the images, and that's those particles. But of course, you can see the snow is not nearly as intense as the previous examples that I've shown. So these were relatively small in comparison events. But you can also see a lot of this stuff here wiggles. That's actually they're huge waves that are created that are traveling through the solar atmosphere. This was actually sort of heart-shaped. I used this on Valentine's Day. And see, again, these particles, this event here, these particles were left over from that previous event. They can last for quite a while. Here's another, this was almost an X-flare, but you can see material actually coming out. And this dimming, so you see here, what I mean by dimming is watch that area. You see it gets dark because material is blown out, and so there's not as much stuff to glow, basically. So you're seeing the material on the surface leaving to go out into space, and then you saw the smoke-like features in the coronagraph. That's the material, the CME, escaping. Not quite as big of a dimming, but you may have seen here that whole side of the sun right there ripples because it's creating these huge waves that are traveling. So I'm going to end with kind of the status of where we are. So for the solar cycle, because when the solar cycle is at its peak, when sunspots are producing the largest amount of activity, in particular those huge blobs of material, those coronal mass ejections, those are what is driving, that's the primary driver of aurora. And so remember, the original estimate was late 2024 to really mid 2025. Right now, we think we are probably at one of those peaks, the peak of the northern hemisphere. So there's another peak that's going to happen. Those peaks are usually somewhere, it actually can be as little as 6 months, but they're usually about 1 to 2 years apart. The north seemed to have peaked in December. We think the south may be peaking soon. There's uncertainty about that because the Earth is tilted, we're not looking directly at the sun. We're looking, depending on where we are in our orbit, we may be looking down, or the sun may be at a different angle. So we have particular times of the year when we can see it better. And the other thing, just to give you an idea, again, we rate flares. C flares are smaller flares, M flares are kind of medium flares, X flares are the largest. There's a lot of M flares. We've had about 600 so far, and that's more than twice the last solar cycle at this time. So this cycle has definitely far surpassed the last one. So there's a lot more to come. The other last thing, and this is a little bit of, there's some research on this, it's not completely certain, but it looks like there's strong evidence that, and I don't know why, but there's strong evidence that odd cycles, okay, we're in 25, so that's an odd cycle, that majority of the activity comes after the peak on the downturn, a couple of years after we reach the peak. So we may be up for some really exciting stuff coming up. You guys are hopefully gonna get to see some really incredible light shows. That's what I'm hoping. So, and I'm hoping you do a really good job of continuing to record them. So, so there's a lot more to happen. The sun is very unpredictable at times. I mean, we have to remember that we think we know a lot about it. We've been studying it, in the space age since the 70s. We've been counting sunspots for a couple hundred years, but it's been around for billions of years. So the things that we think are normal, we really don't know if they're normal or not, or if we're just seeing a little small bit of what's going on. So that makes it exciting. So keep your eyes up in the skies at night. There's going to be some really cool stuff coming, and you probably see a lot of it in the news, but I expect there's going to be some really exciting solar activity to come in the next couple of years. So thank you.
All right, thank you, Alex. I'm going to let you hold on to that mic. my cortisol levels are starting to decrease with the feedback going away, so I want to keep it that way. And I'll take some questions from the audience.
Yes, sir.
We have to use the mic for the Zoom attendees, so I'll bring it.
Yeah, the quick question I have is, what is the typical velocity of a coronal mass ejection, and approximately how long does it take to get from the sun to the Earth?
Great question. Great question. So let me step back. So I'll give you a couple of things. So remember the solar flare? That's light. That takes 8 minutes. Okay. The coronal mass ejection, anywhere from 1 to 3 days. So an average coronal mass ejection would probably be 800 to 1,000 kilometers an hour, which is a little over 1 million miles an hour. Sorry, kilometers per second, which is a little over 1 million miles an hour. The fast ones, the fastest one I've seen is about 3,500 kilometers per second, which is on the order of 8 to 9 million miles an hour. Those, the fastest ones, take about 17 to 18 hours to get here. But I will add one important bit. So we know it's coming, okay? We know even, with 17 or 18 hours, you're thinking, okay, well, I know it's coming, so maybe I know what to expect, okay? There's a lot of uncertainty, just like following a hurricane, deciding where's it gonna reach the land. But there's one important feature that we don't actually know until it gets very close to us. So again, remembering it's about the magnetic field. So here's the Earth, okay? And the Earth has a magnetic field in front of it that's pointing up or northward. So here I am, a CME coming along. I actually have my own magnetic field, my own internal magnetic field. So what if I'm a CME and I'm coming along and my magnetic field is like this? Remember, when you have bar magnets that are oriented the same way, they repel each other. So the energy is not easily transferred into the Earth environment. But what if I'm a CME coming and my magnetic field is pointed this way, downward? Well, opposites attract, okay? And a lot of energy is going to flow in, and then you're going to get a much bigger storm. So thank you very much. So that's an important feature. And the difficult part is we measure that magnetic field of that CME when it passes a spacecraft. The closest spacecraft we have is only 1 million miles away. The sun, remember, 93 million miles away. That's not very far. So we actually don't know the orientation of that magnetic field until it's here. We have 10, 20 minutes maybe, something along those lines. So that's a big challenge.
So the Earth poles flop, I think it's about 1 million years period, something like that.
It's somewhere, we were talking about that tonight at dinner, somewhere around the scale of hundreds of thousands of years, though some of the flips have been millions of years.
So they think it might be headed that direction.
Correct.
So what happens when the poles swap on Earth to the ejecta?
Well, if they flip, then it means that the southward magnetic field CMEs are the ones that are going to bounce off, or
Doesn't it collapse before it flops, or?
No, the magnetic field never goes away. What happens is magnetic fields of the sun and the Earth are primarily kind of like a bar magnet. They have primarily a north and a south. However, they have other parts or other components that are weaker that are in other places. And as it moves, I actually had a video, I decided to take it out because it's kind of complicated, but when you look at the way the sun's magnetic field changes, that gives you an idea. It starts off very, northward and southward, but it kind of spreads out into little bunches of magnetic field around the sun, and the same thing around the Earth, and then eventually will form back on the other side, flipping. But when that happens, it's still there, it's just very weak all over. But you might expect, and we don't fully know, that we would have little patches of aurora all over the Earth.
So not the end of civilization.
It is not the end of civilization, yes. So anything you've heard about that, it's bull hockey, it's not going to happen. Now, is there a relationship between mass extinctions and things like that? Maybe. I'm not an expert, I'm not really sure, and I had a discussion about this at dinner, but as far as I've read, there's no evidence that there is a connection.
We have a question here in the back of the room. Alex, back here.
Okay.
Do you have any idea as far as if time of projection, if we had something like another Carrington event? Massing?
Okay, well, that's a great question. So the question was about the Carrington event. Okay, so I talked about some of the big superstorms, 2003, 1989. The biggest one that we have on record kind of in historically modern, somewhat modern times within the industrial age is 1859, end of August, beginning of September. Richard Carrington, astrophysicist in England, was looking at the sun, looking at a sunspot, and he ended up seeing the first solar flare. And then not too long after that, there were huge disturbances in the Earth's magnetic field, and aurora was seen to very low latitudes. So it was an extremely strong storm. We didn't have the kind of infrastructure that we have now, so the impacts were nowhere near what they would be today. And estimates are that the impacts, if a Carrington-size event hit today, could be billions, perhaps even trillions of dollars of damage to the we don't really fully know. But the question being, when is it going to happen again? Just like a 100-year or 1,000-year flood, maybe it's something like a couple 100-year event, so it's very possible that we could see one again. It's so difficult to make those kind of estimates because we have so few examples. I have read some papers that make estimates that it would be somewhere around 12 to 15% chance. But I will say the farther along we go, the higher the probability ultimately is that we're going to see it. It's sort of like seeing a large earthquake or a large, flood or something. The longer you go from it, the higher the chances ultimately on average that you're going to see a recurrence. So I know that's kind of a wishy-washy answer, but the ultimate answer is we really don't fully know. But it will happen. That is a certainty. Whether it's going to happen tomorrow or 100 years from now, that's not so certain, but it will happen again, and perhaps even bigger. We've seen some in other types of historical paleontological records that dwarf the Carrington event by 3 or 4 times. Yes, sir.
I think I've read, and is this true, the particles, the snow that's coming, is that mostly protons? Or
Mostly protons, yes. Yeah. We can get electrons, and the electrons, we have those more frequently, and electrons actually can charge up spacecraft. So, just like when you have your sock feet and you go across the floor and you touch the doorknob and you shock yourself, built up static electricity. The electrons can build up static electricity basically on spacecraft, and they can randomly discharge. So they call those killer electrons. But the ones that you saw, the really dangerous ones for astronauts and other types of instrumentations, those are protons, yeah.
Take a few more questions in the room, and then we'll move to online questions.
Yes, I had a question about what are the primary elements involved in plasma?
Do you mean for specifically the solar plasma, or?
Yeah, yes.
Well, for the sun, it's primarily hydrogen and helium. Now there are heavier elements, and it actually turns out that some of those images that you saw, the ultraviolet, or the actually extreme ultraviolet, those are actually, one is created by helium, but the rest are actually created by iron. So there is oxygen, nitrogen, iron, silicon, magnesium, a couple other elements. They're very, very less than 1%, but they still can produce that, huge amount of light.
Okay, thank you.
Okay, any other questions in the room?
There's a couple.
Given that this year's solar maximum has come earlier and been more active than was initially predicted, have NOAA and NASA been looking at changing their models as to how they predict these things?
That's a good question. I don't know. I will actually say that there's a new model that's been put out by a friend and a colleague of mine, or two of them, Bob Lehman and Scott McIntosh. And they actually did a pretty good job of predicting. So they were actually on that plot that you saw, and they were pretty close on the mark. Whether or not NOAA and NASA are going to accept their model, I'm not sure, but their models are peer-reviewed, and relatively, relatively robust. So I think that I think they have to. I really do. I've seen some interesting papers. It's amazing how many predictions typically come out every time there's a solar maximum or during solar minimum. Usually 50 to 100 different predictions come out, and about half of them are, they're almost all wrong, and about half of them are really wrong, and about the other half are kind of so wrong. But we don't do a very good job of predicting. So it may be that the new models by McIntosh and Lehman and others may be something useful moving forward. But the problem is we're not going to know until we have a couple more cycles. That's the difficulty. The other thing that's difficult about the solar cycle is, while I'm saying we may be in solar maximum right now, we almost never fully know until about 6 months later, when we can really go back and see, the shape and how it's moved. So typically, the timing is really set about 6 months later. Like, that was solar maximum.
Any questions on Becky's side of the room? Don't want to forget about you guys. Then we'll move on to online questions.
Thank you. I have a question as a practical one for Aurora watching. And I use Aurora now. And pretty much if I see a lot of sunspots, that tells me, okay, make sure you go out and check. But it really is that a good one? Is there a better prediction than that particular app? And I find I can go out when it says there's going to be none and just happen to see
Right.
them.
Well, it is definitely complicated, and so I'm gonna do a little bit of shout out. So my colleague Vincent Ledvina has actually put out some nice blog posts about the Aurora guy, about how difficult it is and some of the ways that you can look at it. Basically, looking at the sunspots is a first step. However, there are a lot of things that you need. Generally, you need to monitor. It's not just, the sun is always putting out this constant flow of material called the solar wind. And so that's actually can also produce aurora. So you will see bursts of it. It turns out that the sun occasionally has these patches that are sort of dark. And that's actually where the magnetic field kind of opens out into space. And because of that, there's less stuff around them. And it basically is like a fire hose. When those dark patches move like this, they're spraying out fast solar wind, and then eventually it'll pass Earth. So that's one of the things. Now, the most dynamic is going to come from these CMEs, but where you're going to know what's happening is the CMEs, not the sunspots. Because even looking at the sunspots is not going to necessarily tell you if there's a flare. But having said that, if you see a large sunspot that's near the central part of the sun, and you have a very large solar flare, solar flares and CMEs can happen separately. However, the stronger the flare, the better chance it's got a CME. And so if you see one of these really big flares right near the center or this area, then there's a really good chance there's a CME coming straight at you. One of the things that you want to look for when people talk about it is what's called a halo, because that typically means the CME is headed towards you. It's very challenging, though, because even though you may have a sunspot over on the edge and it looks like the CME goes this way, there are a lot of factors that can sort of push it to the side, you know. So you really monitor looking for halo CMEs. I mean, I am by no means the best place, but I do blogging in the morning on a place called earthsky.org, and we do talk about that. You know, I try to take the NOAA predictions as well as NASA, because they both will do forecasts that are sometimes the same and sometimes different. But we try to look for those CMEs that we know are coming towards us, or at least have a strong component coming towards us. And that's what's going to be the key thing you're going to first look for Aurora. And then you get down into the nitty-gritty, and it gets more challenging. And then, of course, the other huge factor is just the weather. That's the worst factor sometimes.
We're going to switch gears into online questions. We have 172 people online, which is great. And there are a lot of questions, so I won't be able to get to all of them. But one from Charissa on Zoom: could the solar maximum increased activity affect researchers using remote sensing?
Yes, yeah. I mean, I guess it depends on the kind of remote sensing, but absolutely. There's a couple of things. So depending on, and I'm certainly not an expert on the various, especially a lot of the earth science remote sensing, but there are a lot of issues that can be impacted, in particular, certain communication wave radio bands. The other thing that's a huge, actually maybe potentially a bigger factor, is GPS. GPS is very dependent on the status of the upper atmosphere. And so GPS, it's not so much that GPS is knocked out, but its accuracy is off, and it can be off by a lot. And that impacts a lot of things, not just things like the remote sensing, but in general, it's the timing. You know, that impacts financial transactions, for example. But the GPS accuracy can be off. So if you're dependent upon GPS for timing and whatnot, that's going to be a huge factor. So unfortunately, it's a bit complicated, and it really depends on what the remote sensing is that you're doing.
All right, great. And I apologize to everyone online they have so many great questions, so I'm just going to ask one more from Doug on Zoom. Can you see solar flares and solar mass ejections before the high energy particles reach Earth? How far in advance can you tell a large mass of high energy particles is on the way?
Okay, that's a great question. So, well, the flare typically comes first. The flare does usually come first. So you see the flare. When you see the flare is here because it's light, and you're seeing that first. We're actually seeing the coronal mass ejections in images at the sun. So that image is then transmitted back to Earth. So we see them pretty quickly. But usually in terms of when they get here, you know, they're going to take a couple of days to get here. Those high energy particles, for the most extreme events, can get here within a few minutes after a solar flare. So we can see them very quickly. And we actually often see them on the images of the CMEs at the same time that we see the CME. So as the CME is leaving the sun, the camera that's taking the picture is going to be hit with that snow, those particles, at the exact same time. So I hope that answers the question.
All right. Thank you, Alex. One more round of applause.